anyway, it's a great pleasure. I want to introduce Kip Thorne. Kip Thorne is a professor at Caltech for many, many years. Beginning in the late, he got his PhD in Princeton in 1965, and after 2 years, he came back to Caltech. He's been there ever since. He's an expert in many, many things. Most recently was recognized for decades of work, both in theoretical calculations and actually getting something to happen and getting LIGO, the gravity wave detector, to work, and in the 2017 Nobel Prize that he shared with two of his colleagues. So he's had a very long, distinguished career. It says that he's been good friends with other notable rock star scientists like Carl Sagan and others, Stephen Hawking. But he is going to tell you about his involvement in a movie that seems to have captured the imagination of many people in this audience. I saw it once on an airplane, and I was so enchanted that it wasn't a CD, the Blu-ray disc, and saw it again the next night. Kip has seen it 10 times.
No, I've seen it 5 or 6. Dudamel saw it 11.
Okay, the conductor of the New York Philharmonic Orchestra has seen it 11 times. So if you haven't seen it 11 times, there's more. But anyway, so it's, I'm thrilled to have him here and willing to tell us about this, and it's going to be a fascinating story. So welcome, Kip.
Well, thank you, Steve. Can you hear me in the back? Okay, good. So I was really a bit surprised, more than a bit surprised, when you asked me to come and give this talk about this topic. After all, this movie's 10 years old. But I have come to realize recently that it is, in some circles, a cult film. I have friends up in Eureka, you know, that's that town at the northern end of California, who sent me a photograph of their big, fancy, ancient Arcada theater. During the period between Christmas and New Year's, what did they do to try to bring in the crowds? Well, they had 2 concerts by the local funk band, Diggin' Dirt, and a performance of Interstellar. So Interstellar ranks up there with the local funk band, Diggin' Dirt. That's really good. So let me tell you a little bit about the making of Interstellar. It began with Carl Sagan, who telephoned me in 1980 and said, Linda Obst, who's a friend of his, who is a nascent movie maker, she was just working on her first film, which was Flashdance. She wanted to have a blind date with me. I was a bit shocked. I was single at that time, and so I went out with her. The romance went nowhere. We became close friends, and I was too nerdy for her, and she was too high-strung for me. But we became quite close friends, and so 25 years later, she called me up and said, "Would you like to brainstorm with me for a movie?" And I said, "Yes, of course." I thought this would be a great opportunity. 1, it would be fun. 2, I would enjoy working with Linda. And 3, that perhaps this could work to inspire people about science. How else could I reach out to what turned out to be the sale of close to 100 million tickets around the world? Except through a movie like this. You're not going to, as a professor, touch 100 million people in any other way except a movie like this. So I said, sure. And so we sat down and wrote a treatment for Interstellar. Treatment is a description of the story, of the characters, and in our case, a very detailed description of the science that was built into the movie right from the outset. Linda is well connected, and so she brought on the following February 2006 Steven Spielberg to direct the movie. And so when I had my first meeting with Steven, Linda, and I laid down to him what I would like to be the guidelines for this movie, that nothing in the film will violate firmly established laws of physics, or our firmly established knowledge of the universe, and speculations about poorly understood physical laws, such as quantum gravity, and the universe will arise from real science, not just from the fertile mind of a screenwriter. And he said, yes, he liked that. In fact, this was one of the reasons he wanted to work on this movie, do something very different from what he had done before. And so we were off and running. It took a year to find a screenwriter. Stephen and Linda chose Jonathan or Jonah Nolan to write the screenplay. And so I sat down with Jonah. He was a real bright guy, but didn't know much science. So I gave him a large stack of science books written at the appropriate level for a really bright person who doesn't know any science. And then he brainstormed with me on the science to go into the movie, expanding greatly the science that Linda and I had put into our original treatment. We went through 2008 to 2010, 3 drafts of the screenplay. And then June 8th, 2010, I remember it vividly, Steven Spielberg dropped out. Steven's style is to carry along more films in the early creative phase of the movie than he can possibly make, and then choose among the ones he's carrying along which ones to actually direct. He had a choice between Lincoln, the famous movie about Abraham Lincoln and the freeing of the slaves and the events that surrounded that, and Interstellar. He chose to do Lincoln, which I think was the right choice for him. And so we were left with no director. On the other hand, Christopher Nolan had already told Linda Obst that if Spielberg dropped out, then he might want to do the movie. But Chris's style is completely different. He only does one movie at a time, and he doesn't decide what his next movie is going to be until the preceding movie is out and has been out for 6 months, and then he makes a decision. So we sat for 2.5 years waiting for him to buy in. And after 2.5 years, he did buy in. Brought along Emma Thomas, his wife, is the lead producer on the film. And it turns out Chris has rather strong, much stronger intuition. He was the brother of Jonah Nolan. And so he knew a lot about the film from his brother, who had written the first three drafts of the screenplay. He has rather strong science intuition based almost entirely on browsing the web. He accepted my guidelines about how the science would be handled only to the extent that they do not get in the way of making a great movie. I felt very uneasy about this. But he felt very uneasy about me playing the role of the science police. And so we came in here sort of walking around each other a little leery. But very quickly we came to realize that we could work together extremely well, and that we both wanted to make a great movie, and that we were both willing to compromise to some degree and work together to find solutions to places where there may be some conflict. So he brainstormed with me on the science through 3 more drafts of the screenplay. And by the time we were all done, the final screenplay and the movie preserved Linda's and my science vision. They changed in major ways, almost entirely, the story and the characters. In that sense, then Interstellar is the Nolan's movie, not Linda's and mine. But the science, still very deeply embedded, is joint science, conceived and developed amongst the 3 of us. I made a decision while the movie was under development that I wanted to write a book about the science in the movie to serve the following role: that if people got really excited about science from seeing the movie, they would have a book they could go to learn about the science that is in the movie. And so this would be science education to go along with the movie as an inspiration. And so the book was published simultaneous with the movie's release on November 7th, 2014. I'm going to return to the book, I think, only at the very end. I'm going to come back and comment on the major role this plays in explaining the ending of the movie. But I'll get there. Okay. Some of the movie's science is firm, and I'm going to put an F up here in the corner when the science I'm talking about is firm, and some is very speculative. The speculative in particular stuff involves wormholes. It involves physics of higher dimension, so-called braneworlds. and it involves quantum gravity. These are all areas where there is uncertainty as to just how the laws of physics work. But everything involving black holes, for example, is really quite firm. So let me begin with a piece of firm science. There is a scene early in the movie in which Cooper, it's played by Matthew McConaughey, and his daughter Murph, he says to his daughter Murph, when I'm in hypersleep or travel near the speed of light or near a black hole, time will change for me. It'll run more slowly. When I get back, we'll compare. We might even be the same age, you and me. Imagine that. And this introduces to the audience very early on the idea that time is quite relative. And you see that in the movie as his Cooper's daughter ages from the beginning of the movie at about age 9 or 10 to being in her 90s at the end of the movie. And Cooper has aged hardly at all. One of the first things that Chris said to me as he was beginning to develop his ideas for changes in this story is that he wanted the protagonists, he wanted Cooper to go down and have some adventures on a planet that is orbiting around a black hole that is so close to the black hole that 7 years on Earth corresponds to 1 hour on the planet. It was called Miller's Planet. It's gravitational time dilation, basically a gravitational redshift, the slowing of time near a black hole. When he told me that's what he wanted, I said, that's absolutely impossible. It's just, I mean, everybody knows that's impossible. That's too extreme. There's no way that can be. By then, he already had interacted with me enough to say to me, go do a real calculation and come back. And so I went and I did a real calculation. He was right. That was possible. If Miller's planet is just outside Gargantua's innermost stable circular orbit, if you get the orbit too close to the black hole, it becomes unstable and the planet will fall into the black hole. Then if you're just outside that innermost stable circular orbit, or ISCO, and Gargantua is not spinning, then the time dilation is only about 2/3. That is, time flows at 2/3 the rate on the planet to what it is far away. Nothing like what Chris was wanting to do. But I found if Gargantua spins very fast, the ISCO is moved in much closer to the horizon, basically due to frame dragging effects, dragging of inertial frames into a whirling motion around the horizon. And so I worked out a little formula for working with the so-called Kerr metric for a spinning black hole, that to 1 minus the angular momentum in units of the maximum possible angular momentum, it's a parameter that the relativity theorists call A, is 3√3/16 times the cube of the amount of slowing of time. And with Chris wanting 1 in 60,000 for the slowing of time, that just says you only have to have the spin within a part in 10 to the 14 of the maximum possible spin, and then you're all right. Now, this is astrophysically implausible. But it is not forbidden by the laws of physics. And so we discussed it, and I gave in. And he gets a great movie using physics that is allowed by the laws of physics, but astrophysically implausible. In particular, very early in my career at Caltech as a young professor, I looked at how far you could spin up a black hole by accretion. And if you're accreting from some accretion disk around the black hole, when you get up to within 1 part in 1,000, well, actually 2 parts in 1,000 of the maximum spin, then you start to, the cross-section to capture radiation that's coming off of the disk becomes, and that will spin the black hole down, becomes so huge that the black hole gets spun back down by capturing radiation that's coming off the disk better than it gets spun up by accreting the matter. And so there's, in reality, at least for accretion for spinning up by accretion from a disk, which is the way that we normally think this will happen in astrophysics, this doesn't get any better than actually 2 parts in 10 to the 3rd. So it's implausible, but not impossible. So we went with that. Now, one of the great embarrassments about this movie, maybe my greatest embarrassment, is that there was an effect that I didn't think of that I should have, that should have been obvious. And I didn't think about it because I was obeying the rules. I was not discussing this movie with my colleagues, my physicist colleagues. If I talked with Roger Blanford, for example, he would have quickly told me, look, you've got another problem. This black hole is surrounded by an accretion disk. And I made the accretion disk be the temperature of the sun, very cold compared to what accretion disks normally are, so that the people in the spaceship going around the black hole are not going to get fried by the radiation from the accretion disk. The trouble is that with a blue shift of a factor of 60,000, as radiation comes off the accretion disk and hits the planet, light from the Gargantua's disk, which is in the visible part of the spectrum, gets shoved up to 0.01 nanometers, hard X-rays. And so it's going to be very unpleasant in the scenes. And so that's just by way of warning. I have a number of embarrassments, physics embarrassments in my career. This is one that is not as well known as some of the others. But this is a real embarrassment. If I'd only talked to colleagues just a little bit about this, they would have pointed this out. It's a great embarrassment that I didn't even think of it. And that's real stupidity. I was too busy having fun making the movie. Okay. The orbit of Miller's planet is best described by taking a slice through the equatorial plane of the black hole and then embedding that in a three-dimensional flat three-dimensional flat space to see what the shape of space is around the black hole. And in the case of this very fast spin for the black hole, the usual embedding diagram develops a very, very, very long neck. And so Miller's planet is here. This is the actual physical distance from Gargantua by comparison with, say, the circumference of the black hole. Circumference divided by 2 pi of the black hole turns out, as I'll describe, to be about the same as the orbit of the Earth around the sun. And Miller's planet is up here at a distance that is a few times the radius of the Earth's orbit. So it's quite far away, but it's deep, deep down here in the throat. So this diagram I'm showing in the movie, this is referred to as the 5th dimension, the dimension in the embedding space where you embed, in order to visualize space-time curvature, you embed the curved space in an embedding space. We call it the embedding space as physicists, or sometimes the bulk, borrowing a phrase from modern high-energy theory. Or the 5th dimension is the phrase that is used in the movie. Now, tidal gravity plays a major role in this film. And the tidal gravity that we're familiar with is from the moon, which pulls on the Earth's oceans. Of course, it pulls harder on the ocean on this side of the Earth than on that side. And so this side is pulled toward the moon with greater acceleration than that side, and that's what causes the oceans to bulge. But it's better to look at this from the point of view of the Earth's reference frame, the Earth that falls freely in its motion orbiting around the moon. And then you just see that there's a tidal force pushing the oceans up toward and away from the moon, and on the sides pushing in. And that difference in the acceleration at the surface of the ocean compared to the center of the Earth is the tidal gravitational field, which up to a factor of 2 is just g times the mass of the moon divided by radius, distance away cubed, of course. It's the gravitational acceleration, gm over r squared, then a 1 radial derivative, multiplied then by the radius of the Earth, the separation between the center of the Earth and the moon. So that tells you how much the moon pulls on the Earth surface relative to the pull on the center of the Earth. tidal field plays an important role, as I say. For Miller's planet, similarly, there is a Gargantua. It exerts a tidal field on Miller's planet. And as I'll describe in a moment, we choose the mass of Gargantua to be such that Miller's planet is significantly, but not hugely, deformed. And I'll explain why. Y is tied to the giant water waves that are on Miller's planet that wash over the spacecraft that Cooper lands on the planet in about once per hour. And this is a still from the movie. This is the segment of that segment of the movie.
How long for the engine's case?
A minute or two.
Well, we're going to have it. Coming on. Brand, co-pilot, you're up. Case, load the damn oxygen through the main thrusters. We're going to spark it.
Go to that.
Lock. Depressurize. Engines up.
Now, why don't the waves break? Let's see, did I? Okay. The reason is because they are so-called solitary waves or solitons. These are waves, water waves, in which dispersion, due to the water on the wave feeling the ground beneath it, causes long wavelengths to travel faster than short wavelengths. And so if we decompose that wave into Fourier components, the long wavelengths are traveling faster than the short wavelengths. You know this on the ocean as well. If you look at the at waves on the ocean or on a lake, if they're close to shore, the long wavelength waves are moving very fast. The short wavelength waves are moving very slowly. Okay? But nonlinearities cause the higher part of the wave to travel faster than the lower parts of the wave. The nonlinearity makes the wave try to break. The dispersion makes the wave try to come apart. And it's quite remarkable that the two effects will balance each other and give you a very stable wave that does not break and does not come apart and just propagates along, that has a particular shape governed by the so-called Korteweg-de Vries equation, which you get from the theory of water waves by balancing dispersion against nonlinearity. And the peak of the wave is 5 times deeper than the water depth. The peak of those waves is really high, so the water depth must be pretty deep. But in fact, the Cooper and the people who landed on the planet are walking around on the bottom of the lake, or so they think. It must be that they're walking around on a submerged island, and the wave is coming in from much deeper water that allows that wave then to have this great height and to hold itself together, and they're just on a submerged island. So in the movie, the wave steepness is exaggerated, but not hugely. If you look at that, that's a pretty darn steep wave. It's exaggerated maybe by a factor of 2 in terms of steepness, but not hugely. Now, Gargantua's tidal gravity, as I told you, deforms Miller's planet. The tidal field, remember, is g times the mass of Gargantua, now divided by radius. Now, what radius do you use? You go to the curve metric and you find that you want to use the radius that is circumference of the black hole divided by 2 pi. And then this formula is still correct within a factor of 2. And so when you feed that radius in, since the planet is very near the horizon, you feed that in and put in then the so-called gravitational radius of the planet. This is the actual formula. Even for a fast-spinning black hole, that same formula holds for the circumference around the equator. Then the tidal field has some factors of speed of light and gravitational constant divided by the mass of Gargantua squared. So small, low-mass black holes have far stronger tidal fields than big-mass black holes. If you're going to fall into a black hole, you want to survive to tell the tale, at least survive to go all the way through the horizon. You want a great big black hole. We want a black hole that is significantly deformed for a reason I will explain in a moment. That means that the Gargantua's tidal field must be about the same as the planet's tidal field. The planet is being held together basically by its own tidal field, and it's being torn apart by Gargantua's tidal field. So you want the two of them to be about the same. Since this planet is much like Earth, we don't ever notice the tidal field of the Earth's own gravity on us. So the planet may be significantly deformed, but the humans are not noticing the tidal field at all. And that just works out that the mass then of Gargantua has to be about 10 to the 8 solar masses. That's about the same as a black hole that's at the center of the Andromeda galaxy. And the horizon circumference then works out to be about the same as the Earth's orbit. Those are the numbers that come out. Now, how are these waves generated? Well, the basic backstory, as I see it, is that the tidal field has deformed the planet, and the planet is not yet fully tidally locked, so it's rocking back and forth. And you may say, why is it not yet totally tidally locked? It must have been there for a long time. And the answer is, remember, there's a factor of 60,000 slowing of time there. So a matter of a few days is a huge number of years. And so, in fact, it's still in it's gotten caught in this orbit. It's rocking back and forth, but has not yet ended its rocking due to friction and settled down. And this pendulum-like swing then causes the water to slosh. And you just calculate what is the period of the pendulum. It's about 1 hour, and that's the 1 hour between waves that are now sloshing as these solitary waves that you see in the movie. So that's the story. Orbital motion is quite interesting. The orbital period is seen from afar as 1.7 hours. It's 100 milliseconds is seen on the planet. So here's the planet that begins here, goes around after 100 milliseconds, it's come way back to where it started, and it's going around in an orbit that has the size of the Earth's orbit. It looks like it's going a lot faster than the speed of light. And even the spin of it, it's also then spinning at that same rate because it's nearly tidally locked. And so surely it should be torn apart by centrifugal forces if it's spinning at that rate. In fact, that's faster than the speed of light as well. Well, the thing that we have forgotten is that the spin of the black hole drags inertial frames into motion, and the inertial frames are moving around at essentially almost the same rate as the planet is. And the planet's just fine. It's relative to the local inertial frames, it's not going at a very high speed at all. But that really gives you a deep sense of the power of the dragging of inertial frames around a black hole in an extreme situation in terms of how fast the spin is. Okay. Now, the black hole's appearance, the previous movie that in Hollywood that had shown what black holes look like was the Disney Studios movie, The Black Hole, from 1979. I don't recommend you go watch it unless you want to. Anyway. It's not one of the better movies that Disney has made, even though it did have Ernest Borgnine as one of the actors, who was one of my heroes for his role in the movie Marty. None of you are old enough to have seen Marty, I suspect, but anyway, let's move on. Presumably that was motivated by embedding diagrams for a black hole as seen from a higher dimension, but this is not what it would look like as seen by humans in our universe. And so what then does Gargantua look like? Well, you have a camera, you have the accretion disk, you have the black hole, and you have and what was done was to visualize Gargantua and its disk by the standard method of propagating light rays, null geodesics, from points on the disk through the curved space-time, getting with the light rays getting bent by the gravitational pull of the black hole to the camera. And this was for an IMAX film on an IMAX screen with 26 million pixels, so you have to have 26 million rays. They're very close together. But and so I gave the team at Double Negative Visual Effects, now called DNEG, the equations for this, and so they went in and they built their computer program. And when they built their computer program, they got flickering. And they could not make the flickering go away. They could not get a smooth movie. Just the flickering all over in certain parts of the screen where the light rays had gone close to the black hole, because the tidal gravity of the black hole pries the light rays apart. So these two light rays begin on almost parallel trajectories. And they're for adjacent pixels. And so you follow the rays for these two adjacent pixels out. One of the rays goes to here and the other ray goes to there. And you're sort of dead in terms of getting a smooth movie, pretty obviously. So that was a big problem. Oliver James, who was chief scientist at DNEG, at the visual effects house that was making the movies, which got the Academy Award for the visual effects in this movie. It was Paul Franklin, who was the leader of the visual effects team, got the Academy Award. He had the idea, what we want to do is not propagate individual light rays. We'll propagate 26 million overlapping light beams. So each light beam has a circular cross-section when it reaches the camera, and you follow it back, integrating backward until you hit the disk, with you're having to propagate not only the central ray, but also the ellipticity of the beam and the orientation of the beam. And if they begin overlapping it as 26 million overlapping Gaussian light beams with Gaussian cross sections for the intensity of the light, you come back here, they're still overlapping, even though this one is extremely elongated. And in fact, when we did that, it turned out that the large numbers of these light beams had elongations of more than 100 to 1, some even 1,000 to 1, due to the tidal stretching that was going on. But this handled the problem just fine. And so we wrote a paper together. Paul Franklin, who was the leader of the entire effort, Oliver James, who proposed this method, I, who gave them all the equations, and Eugenie von Tunzelmann, who is the leader of the artistic team that made paintings of the accretion disk, whose the paintings then were used as sources of the light. The disk model that we chose was, as I indicated, an old cooling disk. It's not accreting, no magnetic field or jets, just simple black body emission at 4,500 degrees Kelvin for human safety, except I forgot when they get down on the planet, they're not safe at all. Drawn by the double negative artist led by Eugenie von Tunzelmann. And so this was what it looked like for a black hole with spin, the very high spin that Christopher Nolan wanted. Christopher Nolan looked at that image. He said, no way we're going to use that. He said, it's too lopsided. Audience is not going to understand it, and we don't have time to explain it. You've got, for the purpose of visualization, you've got to slow the spin down. So we slowed the spin down to 0.6 so it would be more symmetric. They added light scattering inside the camera lens, so-called lens flare. Did not put in Doppler shifts. And I said to Chris, we should put in Doppler shifts. He said, no, I don't want Doppler shifts for two reasons. One, they'll confuse the audience if it's really bright and blue on one side and much dimmer and red on the other side. No way the audience is going to understand that, and we don't have time to explain. But he said, more importantly for you, since you're a scientist and this is what you want, the human eye, when you have light that is really bright, like if you're staring directly at the sun, cannot distinguish color very well and cannot distinguish brightness very well when it's a really bright source. And so we want this to correspond to what the human eye would see if you were staring at it. And so he said, we will not, please do not put in the Doppler shift. And so we didn't put in the Doppler shift. And this was the final iconic black hole image. that I think most or all of you have seen before. And the explanation is very simple. Light rays from the back top of the disc's face go up over the black hole and down to the camera, coming down as they arrive at the camera, and so they produce the upper branch of this image. The light rays from the bottom back face come up, they produce the bottom piece of the image, and the light ray from the front of the disk go directly to the camera and produce the crossbar. And so that was the simple explanation. Now, a few years after the movie came out, the Event Horizon Telescope produced this wonderful first image of a black hole. It's seen in the millimeter band, but then turned into an optical image. It does have the brightness on one side and the dimmer on the other side, some Doppler shift effects. And it is rather different from Gargantua, although I've had many people say, isn't it marvelous how close alike they look? Well, I don't think they look very close alike at all. Oliver James, who was responsible for this image, said, well, what happens if you take the double negative image for a thin accretion disk and you look at it from above the black hole instead? So we're just going to move the camera from near the equatorial plane up to the North Pole. And so if you do that, and then you fuzz things out because the Event Horizon Telescope doesn't have very good resolution, lo and behold, now, as the astronomers here may know, this is a bit of a cheat because M87's gas is not even in a disk. It's actually a more volumetric flow and more complicated flow. But it's marginally optically thick, and it gives rise to the same thing, more or less, as you would get by taking a disk image and looking down from above and smearing it out. Okay. Having this marvelous computer program that had been paid for by Hollywood, by Warner Brothers, to develop, we thought, wouldn't it be fun to just explore gravitational lensing of star fields? And so this is what we're seeing. I'll start it over again. So you are seeing an Einstein ring, a sequence of Einstein rings if we had the lights turned down. And I don't want to take the time to do that. With weird motions of the stars. This is what you would get by taking the camera and moving it in orbit, in the equatorial plane, in orbit around the black hole. And the key issue is that if you take the past light cone of the camera, that has caustics as the light rays go around the black hole and to the other side. They cross over each other and create caustics on the structure of the past light cone of the camera. Wherever that caustic intersects with the plane of the stars, which is the so-called celestial sphere, put all the stars on a sphere very far away, then that caustic is a very special place. Its image is the so-called Einstein ring, these rings where you see strange motions of stars, and you actually see images created and destroyed in pairs. And it's really quite interesting then if you play with the theory of imaging and caustics and the theory of catastrophes, particular kinds of structures of caustics. This is all played out, and in our article about how we did how we propagated the light beams instead of light rays, we also discuss all of this business. And we published that in Classical and Quantum Gravity, and perhaps not surprisingly, by a huge margin. This is the most downloaded paper that's ever been published in Classical and Quantum Gravity. Interstellar's Wormhole. Let me just see how I'm doing on time. Okay. The Interstellar's Wormhole reaches from the vicinity of Saturn to the vicinity of Gargantua. And we know there are severe problems with wormholes, and I'd like to discuss them. Wormholes self-destruct if you just leave them to their own devices. So if you have a photon trying to travel through a wormhole, say this is a wormhole described by the Schwarzschild metric, for example, or the Kerr metric, it only gets halfway through and the throat pinches off and the photon gets caught and lost. So nothing can travel through a wormhole. It's just wind up with two singularities on either side. In order to hold the wormhole open, then it is necessary to fill it with what I like to call, when talking with non-scientists, exotic matter, matter that has negative mass or energy and therefore repels gravitationally. It violates the so-called average null energy condition. You integrate the energy density, basically, through the energy density that would be seen by an observer moving at nearly the speed of light. You average that through the interior of the wormhole, and that has to be negative in order to guarantee that the wormhole doesn't pinch off. The average energy, then, so that's the issue. The average energy density is seen traveling through the wormhole at light speed must be negative. Now, it turns out that it is possible, at least in principle, to get, it's possible in practice to get this kind of exotic matter thanks to vacuum fluctuations. And so I want to say just a little bit, motivated by this, about vacuum fluctuations. So if we take a box and remove everything from the box that we possibly can remove, we're left just with vacuum fluctuations. And so if you could see that this has changed a little bit, you see some vacuum fluctuations inside of here. These vacuum fluctuations are ubiquitous in the universe. There's no way to get rid of them. An example, and they play a major role in astrophysics and in science. An example is the Big Bang birth of our universe. It is, the conventional wisdom says that vacuum fluctuations came off the Big Bang and that they were amplified by the inflationary expansion of the very early universe and gave rise to the cosmic microwave background and to all the matter and everything that we see in the universe, ultimately caused by vacuum fluctuations amplified by inflation. Another example, Hawking radiation from a black hole is just vacuum fluctuations amplified by going near the black hole and then escaping. Example, a laser beam's photons. There's photon shot noise, and a standard formula of photon shot noise for a laser beam, the cleanest, most quiet beam you can make. That photon shot noise is precisely caused by vacuum fluctuations beating against the laser light. So random arrival caused by beating of vacuum fluctuations against the steady laser light. Now if you then take the vacuum and you lend some of the fluctuations from this region to that region, the region that did the lending becomes exotic. The renormalized energy density of the vacuum fluctuations is 0 or exceedingly small if it's responsible for the so-called cosmological constant for dark energy. So it's just regarded as 0. Then if you lower them, the vacuum fluctuations in one region by lending it to another region, that has negative energy and presumably anti-gravitates. And that, in fact, is the key. This kind of formation of negative energy of vacuum fluctuations is the key to modern quantum precision technology, which is central to LIGO's development at the present time. It's viewed crucially in LIGO today, the so-called frequency-dependent squeezing in LIGO, which is a manipulation of vacuum fluctuations that are responsible for the quantum noise in LIGO. So today, quantum precision technology is something that goes hand in hand with quantum information, quantum computing, quantum cryptology, quantum precision technology. And at Caltech, we have a new center of quantum precision technology that's our quantum precision measurement that has been started, and we're building a new building in which the laboratories will be used just for further developing quantum precision technology, such as has gone into LIGO. Okay, so vacuum fluctuations are ubiquitous. We now know as scientists how to manipulate them for very high precision measurement. And so all we want to do is hold a wormhole open by manipulating them. Okay? And so the key is that you begin with two electrically conducting plates. if they're electrically conducting, then the tangential electric field is suppressed between them, and that lowers the amount of vacuum fluctuation between the two plates. And so the region between the two plates becomes exotic. It has negative energy density. That's the so-called Casimir vacuum. Well, what we want to do is take a wormhole, and in the throat of the wormhole, put two spherical conducting spheres. They look like circles, but they're really spheres because I've suppressed one spatial dimension. And we have the electric field reaching out from these plates on the two sides to hold the plates apart. They're charged a bit, and so that they can be held apart by the electric field. And what we want to do then is we know that between those two spheres we have exotic matter, which contributes a negative amount to this averaged energy density when you go through the wormhole. But you do have the problem that the energy of the spheres plus that of the vacuum in between must be negative. The electric field contributes 0 to that integral, and so it contributes nothing at all. So all we have to do is guarantee that the spheres have an energy that is positive but does not overwhelm the energy that's in the vacuum in between. Well, there's been extensive quantum field theory research in curved space-time to see whether or not you can construct, motivated by this simple example, whether or not you can construct configurations that violate the average null energy condition. And the conclusion is likely not possible, and therefore wormholes probably always collapse, that even with a very advanced civilization can't hold them open. We don't know for sure. This is not definitive. If you want to read about it, there's a lovely little book by Everett and Roman called Time Travel and Warp Drives that gives all the technical references and describes this, however, in a semi-technical way that's understandable by, I think, everybody on this audience. Interstellar is a wormhole. For visualizing the Interstellar's wormhole, I constructed a 3-parameter metric for a wormhole. Oliver James incorporated it into the computer program for visualization. Eugenie von Tunzelmann and her artist friends drew paintings of what it looks like on the other side of the wormhole. We propagated light beams through the wormhole, and Christopher Nolan looked at what the images looked like as a function of the shape of the wormhole. And he chose the shape of the wormhole that gave him the image that he wanted for what you see looking at looking through the wormhole. And so here is the wormhole as seen from outside, and it is a very short wormhole, it turns out, but that is speculative only in the sense that it's speculative whether wormholes exist or not. This is done by propagating light through the wormhole. And so in the American Journal of Physics, we laid out for students how to make images like this by propagating light rays as opposed to light beams. That's much simpler. And the equations are really fairly simple and readily accessible by junior and senior undergraduates if they want to make images what it looks like to look through a wormhole. And then, my friends at Double Negative then for Christopher Nolan made a movie of what it looks like to go through that wormhole. Saturn is here. Saturn is far away. It looks, I'm going to stop it for a moment. Saturn looks big, but it looks about the same size as the wormhole. The wormhole is really a few kilometers across, and of course Saturn is enormous. But Saturn is very far away, and the wormhole is gravitationally lensing and distorting the image of Saturn. So there's one image of Saturn here and another image of Saturn over there. And now we're going to go through the wormhole and see what it looks like to go through such a wormhole. And this is what they sent from Double Negative to Christopher Nolan and me to look at in preparation for depicting in the movie the trip through a wormhole. It wasn't that exciting. Chris phoned me up on April 10th, 2014, very memorable. He said, "We got a problem. The trip through the wormhole has to be more exciting than that." And so this is the one place where major artistic license was taken. This is the way it would really look right until Cooper pushes the joystick to go into the wormhole. You get the idea. Now, a major role is played in this movie by what physicists call braneworlds, or general relativity carried into one higher dimension, one higher macroscopic dimension. Or in the movie, it's called the fifth dimension. So that here, to visualize this, I suppress one of our spatial dimensions of our universe. Our universe then is shown as a plane instead of as a three-dimensional volume. You've got east, west, north, south depicted here, but not up, down. Instead, you see out, back, going into the bulk, going into the fifth dimension. It's the fifth dimension, of course, because time is the fourth dimension conventionally, so the fifth dimension is a spatial dimension. 1, 2, and 3, and 5 are the spatial dimensions. And so we deal then with physics in 5 dimensions. And now the trouble with gravity in 4 space dimensions, if the space dimensions are flat, or if the fifth dimension, that is the fourth space dimension, represents then a 4-dimensional flat space, then the inverse square law for gravity, if you have a black hole here, its the gravitational force will spread out into the bulk as well as into the 3 dimensions of our universe. As a result, instead of having a 1 over r squared law for gravity, we have a 1 over r cubed law. And of course, that is not very acceptable. That's not the way things operate. And so it was Lisa Randall and Raman Sundram back, if I remember right, early 1990s, I think, around 1990. They proposed that there might be an additional higher dimension, but that it is warped in the form of anti-de Sitter space, or ADS5. So the space-time metric is that of flat space-time, plus the W dimension, which is the fifth dimension, but the amount of space in the the amount of lateral space and time in that fifth dimension is suppressed exponentially as you go up. And with an exponential e-folding time that we choose for this movie to be 0.04 millimeters, basically because the experimental tests of searching for this effect put a limit on of something like 1/10 of a millimeter at the time when the movie was made, things that Eric Adelberger and others were doing. And so that means that if you go out of our universe, out of our brain, and go up by 1/10 of a millimeter, 1 kilometer becomes 100 meters. 2/10 of a millimeter, 10 meters, 3/10 of a millimeter, 1 meter. There's hardly any space up here or down below on the other side of our universe at all. And so with hardly any space there, gravitational force lines are forced to flatten out very quickly on a scale of about 1/10 of a millimeter and run parallel to our brain, and that's how you wind up with an inverse square law. However, that leaves nowhere near enough space up here for humans to go into for adventures in the fifth dimension. And so we couldn't do that. And so my solution to this was to build a model in which there is a confining plane on either side. You go up 1.5 millimeters on either side. There's a confining plane, and it's flat space-time above there and flat space-time below there. And so you have a very thin sandwich that holds gravity in, and then you have a flat space outside the sandwich. And I thought I was very proud of myself. And so I wrote this all up in a technical paper and sent it to Lisa Randall for her praise. Well, she called me up. She said, I have good news and I have bad news. She said, the good news, this braneworlds model was proposed mathematically and explored in technical papers and literature by Ruth Gregory, Valery Rubikov, and Sergei Sibryakov. The bad news is that Ed Witten and others showed that this model is unstable. There is pressure in the confining branes and causes the confining branes to buckle. Like if you take a yardstick and you push on the ends, it will buckle and snap. And they'll buckle and crash into our brain, and it won't be very pleasant to live in our universe anymore. So, well, what do we do? Well, I decided I would give that to Professor Brand to struggle with. And so, in fact, then there are gravitational anomalies in the movie Interstellar. They play a major role. The one that you see most visually is that dust has fallen onto the floor in Murph's bedroom. But it fell down not smoothly. It fell down in a bunch of stripes that were Morse code giving information to Cooper about where to find a particular facility on Earth. But that's the key point, is that there was a gravitational anomaly, that gravity was actually pulling things that fall into these stripes. Very weird. So you watch. You notice that coin fell onto the stripe. Let's watch again. It fell onto a stripe again. No matter how many times I play this, it always falls onto that stripe. So there's a gravitational anomaly. Professor Brand struggles to understand these anomalies, together with Murphy Cooper when she has grown up and become Jessica Chastain. And they struggle to understand the anomalies in order to save humanity from a dying Earth. This is a big part of the movie that I'm not going to really discuss the science of. The Professor Brand has a plan of how to save the remainder of humanity. Most of humanity has died out because the Earth is dying. He wants to manipulate the anomalies to temporarily reduce the gravitational constant near the Earth, so that the Earth gravitates much more weakly, just temporarily, in order that with whatever rocket power they have, they can lift space colonies off the Earth to get all of humanity off of the Earth. Now, this is sort of the backstory of what's going on. You sort of infer that in the movie. And the movie gets a little bit wild from here on. But the issue is, there are these anomalies going on. If they can figure out how to control them, maybe, just maybe, they can pull this off. And so there are 16 blackboards in Professor Brand's office that you see in the movie, many of them. If you want to see the rest of them, you'll find them there. Of course, I'm the one who drew the blackboards. In fact, Christopher Nolan told Michael Caine, who was playing the Professor Brand, that his character is patterned after me. Chris never told me that, but I am the one who drew the blackboards. And the blackboards tell you half of the story of how to do this. And this is them trying to figure it out using a variant of the equations of general relativity in 5 dimensions. The other half of the information is inside Gargantua. That other half of the information is something that is referred to as the professor's equation in the movie. It's really the classical limit of a quantum effective action to the laws of physics in 5-dimensional space-time. Something that they could hope to find by going down, visiting the singularity inside a black hole, which is governed by the laws of quantum gravity, and just hopefully, not actually Cooper, but Tars, a very brilliant robot that went with him, would be able to extract the information from the singularity inside the black hole to get this quantum effective action in order to pull this off. Now I come to Christopher Nolan's conversation with me. Fairly early on, he said, I would like this movie. I've long admired Stanley Kubrick's movie 2001: A Space Odyssey, particularly the ending, which is so puzzling, it's very hard to understand. I want to make a movie that is equally hard to understand the ending. But if you're going to write a book about the science in the movie, you can explain the ending. And so there will be some place that people can go to find out about the ending. And so that's the only way you're going to possibly fully understand the ending is by reading my book. But it's inside the black hole. They're going to learn the quantum effective action from a singularity that's inside Gargantua. Turns out that we knew by the time the movie was made that there are 3 singularities inside a black hole. A very chaotic one that's extremely violent, and 2 less violent ones. One of them is caused by everything that falls. If Cooper falls into the black hole, then everything that falls into the black hole after him, because of the extreme time dilation in there, gets smashed down into a thin sheet that is crashing down on him at the speed of light, basically. And everything that fell into the black hole before he went in gets, some of it gets scattered back up into the form of a thin sheet. And he's sandwiched between these 2, quote, gentle singularities. They're just more gentle than that singularity. So the backstory of the ending of the movie involves these singularities. Cooper plunges into Gargantua trying to get this information, hoping he's going to be able to somehow get back out.
Approaching the event horizon. We're side, dipping down beneath it. Not through it.
And if you look above, inside the accretion disk is the external universe. And this is really the way it works out if you do the calculation, propagate the light rays. And I'll leave that to you to think through, that the external universe gets squeezed down inside the accretion disk. Cooper hits the outflying singularity, almost does. His spacecraft gets torn apart by tidal forces that are very strong there. But he gets captured by, scooped up by a spacecraft created by beings that live in the bulk, so-called bulk beings. I said to Chris when we talked about doing it this way, I said, you send Cooper back to Earth on the 3-dimensional surface of a 4-dimensional sphere. He said, no, I'm going to send him back to Earth on the face of a tesseract. He knew what a tesseract was. I didn't know. Tesseract is a four-dimensional cube. And so Cooper, this is with 1 dimension reduced, Cooper gets scooped up into the bulk by this spacecraft that travels through the bulk that is a 4 spatial dimensions of spacecraft built by the bulk beings, have technology far, far, far beyond ours, and travels backward a distance that is less than the distance between the Earth and the Sun, backward, and docks alongside his daughter's bedroom in the higher dimension. So he's on this face of the tesseract. His daughter is inside her room, and that on that face. But in fact, he is now. Well, I'll explain in a moment. Okay. Let me just explain about the tesseract. So we're visualizing, if you take a cube and you look at it through one of its faces, you see it looks like it has these 4 faces there. You're looking into one face. Similarly, a tesseract looks like a cube inside a cube in the same way as a 3-dimensional cube looks like a square inside a square. So this is a tesseract. And Cooper is there inside the tesseract, and he sees his daughter by light rays that travel. Well, this is where his eyes, they travel from his, sees an image of his daughter by a light ray that travels out the face of this tesseract. He sees another image of her looking in that direction, another image looking in this direction, and all he sees 6 images of his daughter with light rays that are traveling through the faces of the tesseract to him. He then, here are 3 of the images looking into her bedroom. Also are extrusions, things here that he pushes on. TARS, the robot, has learned the quantum effective action from looking at the singularity inside the black hole. Given the key equations of Cooper, Cooper is pushing on the extrusions to send the gravitational signals through the bulk to Murph. Cooper is, however, is now there at a time when Murph is an old woman. He's having to send this backward in time by about 80 years or 70 years backward in time. How does that happen? The key is that in the fourth dimension of the tesseract, in the interior of the tesseract, there are closed time-like curves. And so Cooper's signal goes gravitationally forward in time along the edges of these closed time-like curves and working back along the edges of the light cone and back to Murph. This is bedroom time. That's time as seen by Murph. And Cooper is in her extreme future, but he's sending the signal through the interior of the tesseract back to Murph. So that's basically the story in terms of closed time-like curves. And so I want to just finish off. I know I'm slightly over time, but I want to make some final remarks on backward time travel. Okay, so obviously she gets the quantum effective action. She uses it to deduce how to control gravity and save the human race, and that's the exciting end of the movie. But for a physicist, I think closing remarks on backward time travel are in order. So in Christopher Nolan's final version of Interstellar, there's no backward time travel in our universe. Only inside the bulk, inside the tesseract. So the tesseract basically is a time machine for sending signals backward in time through closed time-like curves that exist in that fourth dimension inside the tesseract. But in one of Jonah Nolan's earlier versions that he wrote for Spielberg, there was some rather different science. There was an attempt to convert a wormhole into a time machine by moving one mouth at high speed relative to the other. Or no, I think it was because one mouth was close to a black hole and the other was much farther away. And the wormhole destroyed itself due to vacuum fluctuations flying through it, a mechanism that Stephen Hawking thought would protect chronology. So Hawking gave us a chronology protection conjecture that basically said that if any very advanced civilization tries to build a time machine, it will self-destruct whenever they try to turn it on. And the mechanism turns out to be vacuum fluctuations coursing through the wormhole. And if you want to read about that, go look at my other book, Black Holes and Time Warps. And this is just a picture of the vacuum fluctuations coursing through the wormhole. But I think it's also, I couldn't end this without putting in a plug for my views about information loss in black holes. Okay. If the laws of physics allow closed time-like curves at all in our universe, at the quantum level, then the conventional formulation of quantum theory cannot deal with those closed time-like curves. You have to be able to foliate space-time in a reasonable way with space slices. You have to have a conventional chronology. But Feynman's path integral formulation, that is sum over histories, can deal with closed time-like curves. And so John Friedman, Nick Papastathiou, and Simon, I think it was John Simon, back in 1992, and then in a much very different approach to this, Jim Hartle, using the Hartle-Gell-Mann formulation of Feynman's path integrals that they developed for doing quantum cosmology. Both of these papers told us what happens if you have closed time-like curves. So suppose you have a space-time with an in region that is chronal, time is going up. You have a non-chronal region in here, so you have closed time-like curves in there, and you have a chronal out region. So you temporarily have backward time travel. What happens? The evolution from in to out is non-unitary. Information is lost in the conventional way of talking about information lost down black holes. Nevertheless, probabilities all add up to 1. This is a really very firm conclusion that the quantum theory done in the presence of closed time-like curves with Feynman path integral approach predicts non-unitary evolution. And of course, we have the age-old mystery of information lost down black holes. There are those who believe that it has firmly been resolved. I think that Lenny Susskind is one. There are those who are skeptical that it's completely understood. My view is that perhaps the laws of physics do permit closed time-like curves, at least on microscopic scales. And then information is truly lost when a black hole evaporates because the sum over histories involves histories with closed time-like curves, and unitarity gets lost. Okay, thank you.
Will you take a few questions?
Sure.
So I have the first question. It's staggering that Chris Nolan and you were actually, he seemed to be really engaged in this stuff.
Oh, he is. I mean, so I also consulted, but not at this kind of depth, on Tenet, where he has.
Oh, by the way, if those of you know Tenet has this thing where time goes backward, entropy flows backward, and these ideas are Chris's own ideas. I mean, he's fascinated with them, but he wants to know what do we really know about these possibilities. So can you really take a person and invert their direction of flow of entropy? So that I go into a room and going with entropy inside me increasing in the same direction in time as the rest of the universe. And I come out and and my entropy is increasing in the backward direction according to the rest of the universe. And so I'm an inverted person, and my personal time is flowing backward relative to the rest of the universe. It's his idea, and when he came up with the idea and started to develop it into a screenplay, he calls me and says, "Will you come over? We want to talk for a few hours." It was more than a few hours. But as you know from the fluctuation theorem, it becomes extremely unlikely. We should talk about this.
Well, now as you know, as Feynman told us, a positron is an electron going backward in time. And it happens all the time with positron-electron annihilation. So it's a variant of that. And anyway, the point about Christopher Nolan is that he has a very fertile mind. He reads a lot of science at the semi-popular level on the web. He comes up with fascinating ideas, and then he wants to talk to a physicist about them, and he calls me.
So his next movie is Oppenheimer, and so I'm eager to find out how Christopher Nolan talked to Oppenheimer.
Yes.
Now, I throw it open for questions. Yes?
I guess you talked a bit about how we keep a wormhole open, but like how do you construct a wormhole in the first place? Because if it's like a black hole, then you obviously can't use it, right? Because you're going through a black hole. So how do we create a
So we know that there are very natural ways to form black holes in the universe by gravitational collapse. There don't seem to be any natural ways to form wormholes that I can see. So either they were born at the beginning of the universe, or some very advanced civilization did it by some artificial means. The natural artificial means would be that if there are topological fluctuations in the structure of space on the Planck scale, on the scale of quantum gravity, say, that a sufficiently advanced civilization you could imagine trying to grab some of these fluctuating wormholes and enlarge them to classical size. I don't know quite what the technology is for that. I'm sure it's much farther than beyond us than space travel is beyond the capability of an amoeba, but it's the only idea I've seen.
And is there any particular reason you didn't consider using an Alcubierre warp drive instead of a wormhole?
Can you repeat the question?
So is there any reason we didn't consider using an Alcubierre warp drive instead of wormhole? I think Miguel Alcubierre didn't conceive his warp drive until after we had started working on this movie. Yeah, I know you think that was a long time ago, but I'm an old man. I'm in my 80s. And as I have been telling people, now that I'm in my 80s, I can do anything I want, and so I'm actually writing poetry instead. You can buy my first book of poetry next October, with fabulous paintings by Leah Halloran.
Yes?
You mentioned that the screenplay was changed a lot in moving from Spielberg to Nolan. Was there anything that you were particularly sad that got cut out of the screenplay?
Oh, yes. So in Jonah Nolan's hands, working with Spielberg, there was a prologue in which the wormhole is discovered out near Saturn because a burst of gravitational waves comes through it and is discovered by LIGO. This was a bit of screenplay that was written about 5 years before LIGO saw gravitational waves. And so Chris looked at that and he said, well, it's a lovely prologue of discovery of wormholes, but we don't use gravitational waves anywhere else in the movie, so it's got to go. We've got to have room for the tesseract. However, the day after we announced the discovery of gravitational waves, Christopher Nolan phoned me and said, would you come over to Warner Brothers? I'd like to talk with you. So I went over and we sat down. He talked for an hour and a half about how he could have used gravitational waves in the movie, and he wished that he had. And then after he'd finished that long discussion, he said to me, but there's no turning back to the past. We just have to move forward.
Any other? Let's see. First you, then you. Okay.
How were you able to balance being a professor and working on this movie? Because I'm sure it's very time-consuming.
So for me, it was not all that time-consuming. I mean, I was doing a lot of things at the same time. The movie, we began work on it in 2005. I think the only time that I spent more than a few hours a month on it was when we were developing the visualization software and the equations for doing the visualization. And at that point, then it was a summertime. I spent a good solid 2 months on that with the visualization team. But other than that, for me, it was small amounts of time now and then. I was working with really great filmmakers and collaborators. And so, yeah.
I want to ask, why do you choose a 5-dimensional Wormhole plan rather than other quantum gravity proposal like string theory or tensor network?
Can you repeat? I didn't even fully understand the question. Can you
So why do you finally choose 5-dimensional Wormhole rather than other quantum gravity plan like string theory or tensor network?
So why did we just choose to do 5-dimensional classical space-time instead of some of the more interesting things like you get in string theory with say 10 or 11 dimensions and all the associated physics? I think it's because the goal is to make a movie that will be quasi-understandable by the general public. And talking about a 5th dimension is something that it was possible to convey the idea to the general public, but I think going much beyond what we did would not be possible. In fact, there was a major issue that the studio executives, Warner Brothers, not just with this movie, but with most of Christopher Nolan's movies, were really scared that the movies were too difficult to understand for a general audience and that they would lose money on them. But Chris, by then, had made so much money for Warner Brothers on all his previous movies that they were willing to let him make a movie of this sort that is far deeper in science and far more complicated in science than most anything else that's been done. And he did manage to get away with it. And this epitomized, I think, by, again, his remark to me, I wanted a movie whose ending is very, very difficult to understand, and you can explain it in a book for those who want to really understand it. But he had faith that the audience would be thoroughly entertained and would be willing to walk out of the movie puzzled, continuing to be puzzled about the ending, and we'll just go back a half a dozen or 11 times to try to figure it out. And it's a skill, a movie-making skill, that he is probably the most effective of all Hollywood directors in pulling off. But going beyond the level of higher dimensional science that we were at, rather elementary level, I think he could not have pulled it off.
Yeah, actually, very much in 2001, tomes and tomes of interpretations.
Yes.
For decades afterwards.
Yes, about the ending of the movie.
Yeah, about what was happening in the movie. One last question, and then I have a final question. Yes?
So you had mentioned that on Miller's planet they had a shallow, underwater island. So I was curious what the physics of the wave would have been like once it encountered.
Well, so the wave is very large compared to the island. And so it just diffracts around over the island and is not much influenced.
So I have a final physics question. In this deviation from inverse square law for gravity, which looked like it was about 40 microns, it seemed to be there's no deviation. To an experimentalist, what if I could push it to a nanometer or a submicron? Or the theorist just going to run away and hide and say, no, it's just smaller than that? When will you theorists get nervous if experimentalists could do a Edvosh type of experiment?
I'm not the right person to ask. I mean, I hope that we live in a universe that has macroscopic extra dimension. I think that would be really interesting. And I hope that we get to the point where we actually see the influence of that. I'm not aware of, but I'm not close to the topic. So I can only say that I'm not aware of anything that says that it has to be anywhere near the level of the current limits. But maybe someone else in this room who works in this area.
And if someone wants to understand the chemistry of the fate of Earth, I guess the oxygen was being depleted, nitrogen was taking over, something like that?
No.
I forget now.
No. So let me just say, by way of explanation, that we had working sessions with experts in all the science that was involved in this. We had one with biologists to discuss all the things that might be going on. The choice that was made is that it was simply a generalized lethal blight. Now, a blight is basically a disease that plants get and wither and die. And blights that are all the known blights are either generalized, they can attack a number of different plants, but they're not lethal at all. They just sort of make them a little bit sick. Or if they're highly lethal, they're very specific to a very narrow range of plants. And I mean, that's how the Earth continues to survive. And so the choice that was made, and this was Jonah Nolan's choice, this was in Jonah's version for Spielberg, was that you had a generalized blight that was very lethal, which we've never seen, but the biology experts that we met with said they didn't know anything that would prevent it, forbid it.
So I have one final request, and that is when they put out the Blu-ray at the 20th anniversary, 10th anniversary, that they, on the Blu-ray there's other discs that have all this information. I encourage you to buy that because it tells you the making of Interstellar and all this sort of stuff. But I would like you to be part of the next Blu-ray edition, and you can explain the physics. Thank you very much.
Thank you. on slightly too long. I think they didn't mind.